Fellas, we're here to do a course tonight on intermittent electrical problems, all right? And that's what we're going to do. All right, we're here going over locating and repairing intermittent electrical problems to power, ground, signal circuits, short circuits, open circuits, cross circuits, and feedback. All right, we do complete open circuits, intermittent open circuits, high resistance in the circuits, all right, rust due to rust and corrosion or bad connections. All right, we're going to have a plan of attack. Anything you're going to do, you've got to have some sort of a plan of attack. All right, when you're going to do these things, remember, intermittent problems are just that, they're intermittent. All right, so they're not there all the time. All right, so if you're going to do that, these things have to be done on complete live circuits, all right, in order to test them properly. All right. You're going to check available voltage, including available information, including codes from the computer and wiring diagrams. Now, codes from the computer can lead you in the right direction, but it can also throw you out of the right direction. All right, so just be careful. All right, but determine your test points and possible test results. That's done by looking at your wiring diagrams and understanding what you're looking at. Then you're going to choose your weapon for testing, what you're going to use for testing. Before we go into choosing your weapon, yeah, no. No, next one. You can do that if you want. Yeah, there you go. There you go. All right? Okay. Before we actually go into choosing your weapon for testing, all right, I have a little quiz for everybody, all right? If a battery, we put a resistor across, a 12-volt battery and a resistor across, all right? It's a 12-volt battery sitting there. Let's say we put a 12-ohm resistor across the battery, all right? Right off the top of your head, how much amperage is going to go through that resistor if you put an amp clamp on it?
2 amp, 2 amps.
Oh, 1 amp. I heard somebody over here. 1 amp. That's correct. All right? 1 amp. Yeah. All right. Speak up so I can hear you if I didn't hear you. All right. But if it was 12-ohm resistor, 12-ohm battery, it's 1 amp. All right? Just to get you going on to what to expect results-wise. All right? If you double the resistance, what are you going to do to the amperage? Half it. It's going to drop, okay? So if you put 24 ohms in there on a 12-volt battery, your amperage is going to be down to a half an amp, all right? If you put a 6-ohm resistor in there, what's going to happen to the amperage? It's going to go up. It's going to double, right? From 1 and go to 2 amps, all right? This is something you do in your head just so that all these calculations are something you do in your head just to figure out roughly what you should expect on certain things, all right? All right, getting into choosing your weapon, all right? We use meters, including graphing meters, a graphing multimeter or a regular multimeter, a lab scope, an incandescent test light, or some sort of an LED or piezoelectric tester similar to a power probe. The only two that don't add any load to the system is the meter and the scope. Test lights, incandescent test lights add some load to the circuit, and they're used where the added load doesn't affect the circuit. And even your LED systems with the buzzer can add some load to the circuit. So be careful, all right? If you're going to actually do specific tests, you do it with these, all right? Now, the left side of this chart just goes over multimeter readings, all right? That you can look over later. However, a lot of people are have always asked me about this. This is the readings that you'll get on your multimeter when you use an amp clamp that's converting amperage to voltage, and in your mind you're converting voltage to amperage. All right? So the only thing I'm going to go over is this. We're usually using the 100 millivolt equals 1 amps, or 1 amp on the meter. So if you've got your amp clamp setting at 100 millivolts per amp, and your reading is 100.0 millivolts, you're reading 1 amp, or 1,000 milliamps. If you're 10 millivolts, you're actually 100 milliamps. 1, you're 10. What are you doing there? All you're doing is taking the decimal point out. Taking the decimal point out. Get to 7.5 millivolts is 75 milliamps. All right? So all you're doing is dropping that decimal point. You don't have to do any other conversions or anything else. Forget the decimal points even there. When you're in that range, that's exactly your milliamp. Your millivolts is exactly the milliamps without the decimal point. All right? One last thing. If you're in a millivolt or milliamp range that has a decimal point, any number to the right of that decimal point is microvolts or microamps. All right? We're going over short circuits, broken wires, open circuits, resistance in circuits, and crossed circuits. We're working on shielded wires, twisted pairs, parallel wires. We're working on all these things. Different things to think about when you're going through some of this stuff. For example, shielded wires create a lot of problems. All right? The shielding on the wires, which is grounded, and wires are shielded so that you don't get any interference in the wires. All right? Usually they're shielded in the engine compartment primarily. They're shielding against stray magnetic field. They're shielding against stray voltages and spikes. And the shielding is grounded out. Sometimes you'll find certain sensors might be shielded if a battery cable is run from a battery in the trunk all the way to the front of the car. During cranking, that draws a lot of amperage. It builds up quite a field. So you might find a shielded wire running through the car rather than in the engine compartment. All right, that if it's critical. All right, twisted pair, same thing. When you're working on a twisted pair or you repair a twisted pair wire, make sure you always put that twist back in it. All right, about at the same rate that it is in the rest of the wire. And again, it's for interference purposes because usually the signals that are going through these wires are AC signals, all right, from sensors that develop AC, that put out AC. All right? Now, we talked about the meters you're going to use. And we said the two top meters you're going to use are your lab scope and your multimeter. All right? Now, has anybody upgraded their meter recently to either a Cat 3000 volt or something to do work on the hybrids or whatever, or even their regular meter? If you've updated it recently, you might find a CD in there. And most people think, well, gee, that CD just gives me the operation instructions or user manual. All right? It might be on there also, but if you also have an RS-232 or a USB cord in there, all right, you're missing out on some of the things that meter can do if you're just using it as a multimeter, because this thing can be used as a graphing multimeter. It's used with your lab scope, all right, as a graphing multimeter, and actually gives you graphing similar to what a Vantage would give you. Not a lab scope really, it's similar. A lab scope is a lot faster, all right, but you can actually, if you have a CD and a cord that comes with your meter, all right, you actually have the capability of doing graphing with your multimeter. You're going through the multimeter to your lab scope, to your PC, all right, or your laptop, all right, but you'll graph it right on your laptop, right through that multimeter. All right, so check on if you've updated your meter recently, and they've come out with them for quite a while now, depending on the meter. All right? Again, open circuits, rub-throughs. All right, now it used to be if you had a wire that rubbed into something, it was usually rubbing into metal. All right, and eventually, if that it broke through the insulation and got into the core of the wire, what would happen? You would have a blown fuse. Okay, all right. Nowadays, there's so much plastic in cars, the wires rub through. All right, they'll rub through into the core of the wire, into the copper. All right, nothing will happen right away. All right, but eventually, if it rubs through that wire and there's no more wire left inside, you get an open circuit, right? Corrosion. Now, no wire is manufactured perfectly. Then when they extrude the wire, they pull the wire through, and they pull the wire through a plastic extruder, and it extrudes the plastic over the wire. Now, if it's not run right down the center of the plastic, if there's not enough tension on it, and it happens, things happen during operation, all right, and during manufacturing process. All right, sometimes the copper might come very close to one side of the insulation, almost to the edge. All right, or if there's bubbles in the wire, in the insulation, as it's manufactured, all right, you'll get little specks in the wire. You'll never see them usually. Usually won't see them, but because of the wire vibrating in cars and the flexing in the cars and everything else, sometimes a hole will develop, a pinhole will develop in that wire. And when a pinhole develops in the wire, moisture gets in there, starts corrosion, and then you'll see a puffing up of the insulation, and eventually when the corrosion gets bad enough, it starts to cause intermittent problems to begin with, and then after the intermittent problems, it starts to get a complete open. All right, and to the point that not enough current can flow through there and it'll give you a problem. Also, where wires flex, all right, where wires flex, they create breaks in the wires. That's why we don't use solid wires on cars or vehicles, because where the flexing is a solid wire would break very easily. All right, but flexing indoors, even in the engine compartment, all right, a lot of problems just from flexing. All right, the primary cause of most bad connections in cars are actually poor connections at connectors. Again, due to corrosion, heat, overcurrent, whatever. All right, that's the primary cause of problems. All right, the other cause is rust or corrosion on anything from like eye terminals, ground circuits, anything like that. But let's talk about poor connections on connectors. Now, when connectors are made, no matter what connector you look at, a connector is designed for a specific amperage. Right? When the manufacturers make a wiring harness up, they look at the connector, they decide what gauge wire to use, and they decide what connector to use on it. And depending on, that's why you'll see in a connector or a connector at the computer, some are bigger than others. All right, some will handle more current than others. All right, and the primary thing with all connectors, all right, as the barrel comes down, all right, there's always either a spring tab going down, a spring tab going up, or both directions. All right, there's always something that keeps tension on the pin when the pin goes in. This tension is needed all the time on there. So what happens if somebody sticks a test light in this thing and jams it in there, and they bend back this little edge, that curled edge on there, and it loses spring tension, then you lose connections. All right? Or it may not handle the amount of current and eventually go bad. Or if it goes over current and it heats up, the copper that's in these connectors cannot take a lot of heat. And when the heat builds up, it loses its spring ability. And then it loses tension. All right? And of course, if corrosion develops in there also due to moisture or whatever, you lose connection. Here someone has stuck a test light in this connector, and this was giving intermittent problems because this connector was under the hood of a car, and as it moved, these three were staying connected, but this one here was not. All right, so it's a big problem when people go in with test lights, or even, I'll explain something later to you, all right? Here's another one. This one overheated. All right? Now the tension on this curled edge has been lost. Now I'll just show you the mating connector to that. This happens to be a fan control module. All right? You could see around here where it melted the plastic. Actually the terminal and the module, the male end of the terminal here, and the module was actually working. It would work. But as this moved, it would lose connection. All right? Now, I'll get into later the fix for something like this if you cannot find a new connector. All right? You can fix it without ripping everything apart and taking some solder and soldering something, wrong way, and soldering something onto there. I've seen everything done, but there is a better fix than that for this. All right? Here's a lot of connection problems. All right? Where the connector works its way into a circuit board. All right? Where the tabs come in and then they come down and they get soldered to the board. You don't know how many problems I find where connectors to the board. And the only way to test these is to take the module apart, whatever it is, and test the circuit at the circuit board end. It's the only way to test them. And I've done a lot of it. I have found where many things have gone poor solder joints due to vibration. They're due to vibration. All right? They're due to just bad solder joints to begin with. They're due to vibration is one of the biggest things. All right? We're dealing with connectors at the end of wires, connectors in the middle of wires, and multiple connectors at any kind of junction block, all right, isolation blocks, all right, and they can, whether they go to ground or they're in the car, and there's a lot of these that go to ground in the engine compartment and they're not even sealed. They just go to ground. There's a lot of them out there. And they're quick disconnects onto a block, and the block is grounded. All right? How do you tap in? All right? The most popular way of tapping into a car is the T-pin. All right? I don't like the T-pins. I'll tell you why. I like quilting pins. They have a plastic end on them. All right? They're thinner. All right? But you have to remember something. There's a lot of connectors out there. You might find that a quilting pin is a little thin, all right? You may find that a T-pin might fit it better, all right? Back probing, I always like the quilting pins. Again, they're thinner. You can get them in easier, even though the T-pins do have different thicknesses available. But on T-pins, you see that T on the end? That's why it's called a T-pin, of course. That T-pin swings around because there's nothing to stabilize it. And if you've got a couple of close circuits, all right, that you're testing, all right, you can cause a cross circuit that way, cause problems. That's why I don't like T-pins, all right? But I use the quilting pins and other ones, all right? Sometimes even people, we had last night, people say they use a lot of paper clips. That's good too, all right? The one thing to remember, check when you're putting that into a female connector, make sure the fit is snug but not tight, because if it's too tight, you may be taking the tension or spreading that connector. Okay? I find that all the time. I had car the other day with a transmission problem, and the person, it was a trans shop, and he said to me, he said, I had certain codes in the car. I had done something to the transmission. He said, but then I found the computer was bad. I said, okay. And after he replaced the computer, he had other codes that were not in there before. And he called me up, and I went in and I found that that's exactly what he had used. He used not a T-pin, but he used, I believe it was some pins they gave him with a testing device for going in. And if you looked at the end of the connector, the plastic even when he put the pin in, which was an actual square hole, gee.
Yeah, I had, funny you bring up transmission. I had an Allison training that wouldn't ship right. When I put the T-pin in, shipped perfect.
It took the slack up. It
worked great, and I had to wind up cutting it out, putting a whole new connector.
Right,
So, yeah, be careful.
right. Yeah. Well, on this one, all right, same thing. He had used the wrong size. He went in there and sprung, oversprung the connector, all right, on 4 of them. On 4 of them. I went in there, I took the entire connector apart, I resprung it. I was able to get it to respring. All right. Put the connector back on. Excuse me. They had, now he lost all the codes that he had, but he had another code. But that stands to reason. You know that if a code comes up on a vehicle, the computer checks certain things first. All right? And it might throw a code up and not even check anything else. But then when those codes are cleared, it'll check something else and say, okay, now we've got another problem, and throw another code up. All right. There was another problem inside the wiring harness in the transmission. He had put a new wiring harness on, and they had given him the wrong harness. All right? But that was taken care of, and now the car was fine. But the T-pin, or not the T-pin, but the probing of that connector started this problem, or the second part of this problem. All right. You can use these piercing devices with a tip that pierces the wire. They're very good. I use them if I have to just go to the wire and I can't back probe. All right. However, if you use these or you pierce the wire in any way, shape, or form, when you do that, if it's under the rug of a car or in the engine compartment, make sure you seal it. How do you seal it? What do you use?
Silicone.
Some people use nail polish, but you have to remember something. If you use nail polish, make sure it's an acrylic enamel and not an acrylic lacquer. If anybody is more familiar with bodywork here, lacquer is harder, dries harder, all right, and it actually cracks. All right, the enamel lasts a little bit, is more pliable. All right, but better than anything, use clear ignition sealer, clear battery sealer, or clear electrical insulation in a spray. They all make them in spray. I know BG makes them, 3M makes it, Permatech makes it. In one way, shape, or form. Spray it, you use clear, therefore you're still going to see the wires. If you get overspray on something, it's not going to do anything.
How about liquid tape?
Liquid tape, the reason why, you could use it, but it's kind of tough. You got to let it dry, even though it dries pretty quick. And working on one little point with that brush or whatever, it's a little hard. I like to use the clear. That way it doesn't interfere with the wire. All right? Okay? Here's what we're going to be looking for. We're going to be looking for things like this, where there's corrosion or whatever. All right? These are the things we're going to be looking for. Let's go over them one at a time. All right? This happens to be in a heater circuit. Had 12 gauge wire going in and out of this. and it would be intermittent at first, and then all of a sudden it went completely, overheated. Now here, if you look at this here, you'll see that this was in the engine compartment. This is a splice where we had 2 wires coming in this side, 2 wires coming in that side. Right? In the engine compartment, this splice. Now that wasn't really waterproof. They don't necessarily waterproof them. Okay? But it was in the engine compartment, got moisture in it, and it corroded away. Green corrosion in there. It corroded away. Green, when you see green, it's usually related to copper. Okay? Here's a connector that was under the floor of a vehicle. All right? And this was on an import, Asian import. All that is about a 2-inch wide piece of some type of electrical tape from the factory. This is how they do it. It's not insulated. It's insulated. It is not sealed whatsoever. And this connector, the splice in there went bad. Here's one. If you look closely at this one, you'll see this. Someone did a repair on the car. They used a butt connector. All right. They sealed it with actually the heat shrink that has the sealant in it. All right. But what happened? Too much current went through it for that splice or the connection to take. All right. It just overheated and just puffed everything up and melted everything. All right. Here's a completely formed, supposedly watertight seal, all right, that's extruded, right, along with the wire after the splice, and it's molded right onto the wire. And even that went inside. Now you can't even see it. I didn't see it blow up or anything. But the wires coming out this end down here had no continuity. These had connection to those two, wasn't coming out the other end. A lot of problems with corrosion, water getting in, this other things we're looking for, water getting into cars, following wiring harnesses down, leaky windshields or whatever, and they'll work their way down a harness, the water will just wick its way in and cause problems. If you have something like this, you might see, well, look, those terminals are nice and shiny, but something was in here. It didn't get into the terminal blocks here, but it did get into the relay, and it was oozing out of the relay. Creates a lot of problems. Here's a board where if you look at all the other terminals on the board, they're nice and shiny and clean, but this terminal, all these terminals went to one connector. That one connector ran under the windshield, below the windshield where the leak was. The water followed it in, went right in here. All right? This terminal really got it bad, didn't it? Okay? And what happens if you look, I did have a terminal board here. Maybe I left it in the car. I have this terminal board with me. All right? I'll bring it after break if anybody wants to see it. I have a cutout of the side view because on all these terminations now in the new blocks, you'll see all these lands run. There's another layer underneath that. There's another layer underneath that. There's another layer. There's 5, 6, 7, 8 layers. All right? And then water just works its way into all the layers, corrodes, causes all kinds of problems. We'll get into that. All right? There's the other end of the connector. You can see water got into it, came in. All right? And that's what's left of the terminal that broke off, corroded off. That didn't heat up, it just corroded off. A lot of corrosion, especially under the hood, all right, which have to be cleaned up, and you really should clean them up with something like a tiny wire wheel on a Dremel tool, or even an engraving end on a Dremel tool. Clean them up good, because a lot of times something like this, even stable in 22 isn't going to clean it up that good. Okay? It also in the same board, if you go to one part, you might even see the same thing, where this overheated. Look at the discoloration of that. And that's overheated to the point it won't make contact. But we'll be going over some things you can use to take care of this without replacing the whole board, all right, or the whole block assembly, or attempting to take the whole thing apart and try to get a new terminal in there. All right. Now, my pet peeve out there is shops that call me up and say, hey, I got a short in the car. Can you come out and look at it? And I'll say, okay, what fuse is it blowing? It's not blowing the fuse, the battery's going dead. I said, so you don't have a short? Oh, yeah, that's a short. I said, no, it's not. It's a parasitic draw. All right? So I get a lot of times calls for parasitic draws. And when parasitic draws, I get calls on parasitic draws, I always tell a shop to prep the car for me. And that includes making a test on the battery, charge the battery, prep the car, get it ready for me to test, because I don't want to have to go out there and find a car that's out there sitting at the end of the parking lot. All right, here's the keys to the car, there's the car. You go out there, the battery's dead. All right, you gotta prep the car, you gotta somehow charge the battery, or you gotta do and then you have to wait for the car to time out. All right, so when I tell a shop to prep a car for me to find a battery draw, all right, I want them to do the prep so that after it's prepped, by the time I get there, it's timed out, and it takes about 10 minutes to prep the car. All right, however, when I go and do a parasitic drain test on a car, what happens in your shop? Let's say you do a parasitic drain test on a car, no matter how you do it. All right, I'm not going to tell you whether you're right or wrong, and I'm not going into testing parasitic drains on cars, all right, tonight. But if you do a parasitic drain test on a car and everything tests good, the battery tests good, the alternator tests good, you put a drain test on a car, you put whether you use an amp clamp or whatever you do, all right, and you see after it times out, it goes to 0. What do? Tell the customer, hey, it's not happening now? Bring it back when it's happening. Oh, it comes back you charge the battery, comes back a couple days later, battery's dead again. All right? Well, let me tell you something that I always do now. I don't care who's tested the alternator. I don't care who's tested the battery or whatever. All right? I do my own test on that only after I find no drain. However, I use one function of my multimeter that most everybody's familiar with, but I don't think they've ever used it this way. I've had only 1 or 2 people who've said they've used it this way. All right? All right, here we've got a battery and a starter. All right, we've tested the alternator's fine. All right? Put a voltmeter on the battery and an amp clamp or an amp meter on the alternator. on the starter. All right? All right, we're sitting there, battery's sitting at 12.6 volts, and of course there's no amperage at the starter because I'm just hooked up. What can we tell by that right away about the battery?
Full state of charge.
It should be fully charged, okay?
It is.
Yeah, it should be fully charged, okay? Now, one thing I'm doing, I'm changing one thing. Once I'm hooked up, I push the min-max button on my meter. All right, on my multimeter, for a reason. That multimeter is going to take readings in min-max faster than the display is going to change on the meter. A lot faster. And it's going to catch drops in voltage a lot faster than I'm going to watch that meter change its display. Okay? And depending on which we're going to go over later, depending on the speed of your glitch capture rate on your multimeter will allow you to do certain other tests. All right? This one doesn't matter too much. You can have a 100 millisecond, 250 millisecond glitch capture rate, and you shouldn't have too much of a problem. All right? But I wanted, and I told the people, I want 6 starts of the car. The guy was sitting in the car, the shop owner was sitting in the car, and I said, okay, I want 6 starts. Crank to start, shut it off. Crank to start, shut it off. Do it 6 times. All right? Here's what I found. All right? After the first crank, battery was at 10.5 volts, 240 amps. Seem okay?
Yes.
Okay, seems okay. All right? After about the third crank, all right, my voltage dropped. Starter stayed about the same. Starter looks very stable, doesn't it? All right? But, gee, that looks like it's a little dropping down a little bit. Now, this vehicle was at 4 shops. Okay? Vehicle was at 4 shops. And I'm going to tell you something. This is not, I tried this later on, without min-max, that's not what I saw. I saw approximately 10 point something volts. All right? After the 5th or 6th crank, that's what I saw. Okay? And again, the voltage didn't actually drop very much on the regular display. Now, if you have a bar graph on the bottom, you might see it drop down because that moves a lot faster than the change of the display. All right? However, you want it on min-max, and that's what you'll find. What's wrong with this car? No matter what your battery tester says or whatever, and I don't know what battery testers they used, all right, but that's what's going on. All right? Now, another vehicle, just basically opposite results. All right? Crank the car, first crank, 240 volts, about 10.5, 240 amps, about 10.5 volts on the first crank. All right? After the third crank, went to 440 amps. And the voltage stayed about the same, but of course this guy had put in, now changed several batteries, and now he wanted the best battery, and he was up somewhere around 950 cold crank amps or something like that, you know, put the best one in there, all right? But battery stayed about the same. Look at the amperage of the starter, all right? And after this 5th or 6th crank, my meter went overload.
Wow.
All right? He was thinking the battery was going dead, all right? But it wasn't. It wasn't going dead, all right? So if you find that the starter is not stable, if it's drawing different amperages during different cranking cycles, all right, unless you've got a timing problem or some mechanical problem in the engine, all right, that's what's happening. Your starter's going. And it can wreak havoc with the system. And it's mistaken for, both of those situations were mistaken for a short or parasitic battery drain. Okay? Now, let's get into, we're going to do like an amperage test on these things. And a lot of guys, let's say you're checking a blower motor on a car. And I've extracted a lot. All these drawings that you'll see in this presentation have been extracted from circuits and redrawn, so that you don't see a lot of other stuff in there that's going to throw you off. All right? But let's say here we have an alternator hooked to the battery. Your battery is hooked to ground. Your battery is hooked to a positive system. I'm not concerned right now about a fuse or anything, but a switch. And let's say we're hooked up to a fan. All right? It could be a relay or whatever contact, and we're hooked up to the fan in the car, the heater fan, blower. All right? Now, granted, there are some cars that have very high capacity blowers, but you'll find 40 to 50 amp fuse links on the high blower circuit. All right? They may draw a bit more, but I'm going with a standard, let's say a standard GM blower motor, for example. All right, can anybody tell me what a typical GM blower motor draws in amperage?
20 amps?
That's kind of high. All right, usually it's about 15, 16 amps. All right? All right? Now, the ones that draw 20 and more, above 20, usually have fusible links on them that are 40 amps or even 50 amps. All right, but the ones that are drawing the 15, all right, you'll find they've got a 30 amp fuse on the high blower side. And what do GMs usually use on high blower circuit? 30 amps. All right, one thing about fusing on cars, if you take a circuit and you measure the highest amount of current with the vehicle would normally have on that circuit, all right, and it's a fused circuit, you usually find that, let's say if it draws 5 amps, there'll be a 10 amp fuse. If it draws 30 amps, there'll be a if it draws 15 amps, there'll be a 30 amp fuse. Okay? It's usually double what the circuit normally draws. All right? Sometimes it varies, but not very much. All right? Now, when you're testing, a lot of guys will say, okay, let's turn the key on, activate the relay, turn the switch on, activate the relay, and put an amp clamp on the motor. All right? And what do you come up with? The battery now is sitting at 12 volts because the motor's drawing 16 point something amps. Okay? And you say, that looks okay, right? What happens when you start the car? Voltage goes up. Voltage is going to push more amperage through that, right? All right? Where I was getting over 20 amps, it was varying between 23 to 25 amps. All right? Now, the system's only fused at 30 amps. All right? So you got problems there. So you always have to remember, when you're doing a test, all right, test at normal operating voltage. Whether you're running the car or whether you've got a battery tender on it, all right, make sure that your voltage is right and then watch your amperage, because as that voltage goes up, the amperage goes up. And this is what happens when the amperage goes up for too long. Something like this happens. And when this happens, eventually it just opens circuits. Or else it starts doing something like this to the blower switch. All right, and it takes a while for that to completely go like that. They're actually hold up pretty well, but eventually over amperage causes this problem. That's not a short that causes that. It's over amperage. That's what everything, it still runs. All right, everything still works. It may not work as good, but it still works. Also takes out, if you look in here, takes out relays and PC boards. The same way, over amperage. So check your amperage on things. Now, how does the computer check for amperage? Remember, you've got codes on the computer now. They'll tell you, a code might say check for short or open on a specific circuit. Some vehicles actually say check for overcurrent, over amperage. How do they test for it? They do a voltage drop test. On the output of the computer, they run a calibrated resistor. And it doesn't make any difference whether the circuit is fed B plus through a coil or whatever it is and back to and grounded through the computer, or the computer puts out B plus through the accessory or whatever and goes to ground. On its output circuit, they have a calibrated resistor. And what do? They measure the voltage drop across the resistor. It goes into a comparator in the logic circuit, and the logic circuit will determine whether there's a lamp out, there's a problem in the circuit that may cause the computer to shut down. It may shut the computer down, it may shut itself down from the logic circuit just because there's a problem, and say We don't want any other problem with we don't burn out the computer, let's just shut down. I have that situation a lot, okay? So they measured a voltage drop across a calibrated resistor. There's a calibrated resistor on a circuit board. Now they come like this flat, they come round. Some of them on engine computers, they look like a regular resistor, all right? They're just soldered right into the PC board, all right? But this is one common type that you see, usually not on PCMs, but some sort of body modules, wiper modules, anything like that, okay? Flasher modules, all right? Lighting modules, all right? You'll see something like this, or the round wire ones, all right? All right, now, so we know the computer does voltage drop testing to test circuits. So what are we going to do to test circuits? We're going to do voltage drop tests to test for different problems in the circuit. All right, and one of the ways we're going to test circuit is a voltmeter to ground, which is potential to ground. What are we testing when we're testing with either a lab scope for voltage or a voltmeter? We're testing potential, voltage potential. All right. So it doesn't make any difference on most of these meters whether the connectors are one way or the other way, reversed. The only thing you'll do is you'll get a negative sign on the meter. That's one good thing about digital multimeters. All right. Now if we have a circuit here with a battery, we'll give you everything in here to fuse the switch, and we've got two bulbs. Now one of these bulbs is representing the load, and the other one is representing some resistance. All right, or resistance in the circuit. But let's take first, let's say there are two bulbs, identical bulbs. They could be 194s, they could be 9004s, they could be, headlight bulbs, doesn't make any difference. If both bulbs are the same in resistance, both bulbs are the same number bulb, the readings that we're going to get, that we're working with now, are going to be identical, as long as both bulbs are the same. And it doesn't make any difference what bulbs they are. From a headlight bulb to a 194 bulb, doesn't make any difference. The readings we're going to get are the same. So, if we take a reading to ground and put a voltmeter right there, what should you expect to see? 12 volts, all right? And we're set up here, the way we're set up here now, remember, both bulbs are identical. How about there? I didn't hear. How much voltage? 6. All right? Remember, both bulbs are the same. They're both on. There's a voltage drop between them. All right? If they're both the same, you're going to get half the voltage. It's like a voltage divider. And if they're both the same resistance, you're going to get half the voltage. All right? Naturally, if we go here, how much voltage are we going to get? 0. All right? Now, we're going to take the ground away and go in the middle of the two. 12 volts. Why? There's no current flow, right? All right? So there's no voltage drop at this point. There's no voltage drop. So again, what you would expect to see, all right? We're going over this, all right? And it's a little bit basic, but we're going over this for a reason, all right? When you're making tests in circuits and looking at diagrams, you've got to determine where you're going to make a test point and what you expect to see. All right? And if you don't see that, you better find out why. All right? Now, if you're with the circuit over here, again, you've got no flow, so you're still 12 volts. However, now we're going to do not potential to ground, but potential point to point. All right? Now you take the two lead to the multimeter, and you go from here to here. Okay? Now, the way the circuit is set up right now, all right, what would you expect to see? The reading on your meter would be what? 0, correct. There's no flow, no voltage drop. Now we put the ground back in. Now what do you expect to see? 6 volts, that's correct. Half the voltage, all right, on that part of the circuit. And there to there? 6 volts also, all right? So that's if both of them are the same. Now if one of them was different, the voltage would change, all right? But the fact that there's a voltage differential to show you that testing for voltage differential, all right, you're going to see with different resistances in the circuit, you would see a voltage drop. The fact that there's a voltage there means that there's a voltage drop. And again, if we were, well, I'll go over this the next, but when we test a battery, what do? We load the circuit that's in the battery. We load it with a resistance, all right, whether it be a carbon pile or whatever. We load it with a specific resistance, and we do a voltage drop test, all right? Now, if we're going to load a wire, if the wire has B plus on one end, what we're going to do, if the B plus is there at the battery, all right, we want to bring that wire with a load to ground. And we want to load it with, now GM just came out with a directive. General Motors says all the wires to the computer that go to sensors or whatever can be tested with 5 amps. They want all wiring tested, all the thin, those little wires and stuff, tested with 5 amps. All right? So, if you put a load on there, now, I don't know if anybody was here a couple of times ago when I made up my little tester for testing 5 amps. I took a fog light with an H3 bulb, all right? Now, that draws about 5 amps. All right. If the battery voltage is at 12 volts, it's a little less, but if the car is running or you have a battery tender on it, it draws about 5 amps. All right. So I can hook one end up to either ground or B plus and load a wire. And if I use the lamp, I may not even have to do a voltage drop test unless it's critical. Right? Because if the lamp lights bright, should be fine. All right? If it's a real thin wire, I might find some voltage drop and there really isn't a problem. All right? Because again, the thinner the wire, the more resistance it creates with higher load. All right? So if you've got B plus on this end, you're going to load with a negative load, a load to ground. If you've got ground on this end of the wire, you load with B plus, with some sort of a load. Okay? If you've got wires that split, let's say go to different tail lights or whatever, all right? Whatever it is, if you got B plus on that end, again, you're going to load to ground. If you've got ground on the upper end, you load to B plus, and you're going to check all the splices, check every end point so that you take into consideration all your splices in the wiring. As I said, sometimes the wiring checks good and it checks fine. But you may have a problem at the connector, something similar to this. You may have to go into the module and check after the connector on the PC board. All right? Then get your voltage drop. Now, it might be difficult and almost impossible, or even an impossible task to do it on an engine computer that's sealed. Okay? But if some engine computers are inside the car and not sealed, you can do it on that. And I've done a lot of door modules, things like that, where these things happen, especially on the sliding door modules, the automatic sliding doors and things. Right? Sometimes you have to go to these. All right? Again, as the connectors come through, all right, you may be good right up to the connector, and you're only testing one circuit. If you've got a problem with one circuit, you don't have to worry about all the rest of them. You can look at it, but if you're testing one circuit, do that specific circuit first. Follow it in here where it's soldered to the board, and find where it's soldered in, and go to that end of the PC board, check that solder joint. And what do you find on some of these solder joints? You find things like this here. You find things like this here. All right? Weakening solder, cold solder joints, bad solder joints, fatigued solder joints. Different kinds. All right? Sometimes it's a little hard to see. All right? You got to get good magnifiers and look at them. This one's very easy to see. All right? You see the circles? If you look straight down on it, you see the circles around them? These were giving intermittent problems. All right? Would work, wouldn't work. Would work, wouldn't work. All right? Very easy if you have good magnifiers to see them. All right? Getting back to our doing potential on the wires. Voltage potential with the meters. Now lab scopes you do the same thing with, all right? We'll get into later. But if you're doing potential to ground and you're testing at the load, or if you're doing potential to ground and you're testing at the load, all right, you make sure the voltage is good here. You make sure the ground is good here. If you have a resistance somewhere in that power supply and you're doing a potential to ground, in order to see how much voltage drop you have to first measure and make sure you have good voltage here, and then measure here and say, okay, that voltage isn't right. If it's 12 volts here and 10 volts there, what's your voltage drop? 2 volts. All right? If the resistance is now in the ground side, all right, same thing. You're doing your potential to ground, all right? If you measured at different points of the wire, all right, you'd see a voltage here and ground here. But on this side of the wire, you would see basically what? 0. And you would probably, if there was a 2-volt voltage drop, what would you probably see here? 2 volts. Okay? Now, the second way of doing a voltage drop is not to ground, but point to point, like we did on the other diagram also. All right? Where you're using each point of the multimeter to one side. So in other words, you're still doing the same thing on the ground side, because instead of this going to ground somewhere, you're going to ground on this end of the wire, and you're going to the ground on this end up by the load. Okay? So you're putting the meter in parallel with the wire you're testing. All right? So again, if you're putting it in parallel, so you're actually ground and you're at the load, what should the meter read if you've got a 2-volt voltage drop? 2 volts. All right? If the resistance is on this side, now you do the same thing, but you go from point A to point B. You don't... The same thing, if you had a 2-volt voltage drop, what's that meter going to read? 2 volts. All right? You don't have to subtract. So if you were to ground before, you would have 12 volts here, 10 volts there. You'd have to say, I have a 2-volt drop. If you put the meter in parallel with that wire you're testing, the meter will actually read your drop, your voltage drop. Okay? Now you could do this also with a lab scope. Most guys use lab scopes to ground, all right, and look basically the same thing, all right? Now, again, if you put the lab scope in parallel with it, it will also give you your voltage drop. We'll get into that later. All right. Again, now I've put different things in the circuit. All right. If you got it voltage, doing with constant voltage, and you're doing it to ground, again, measure your voltage at different spots up to your load or at the load, and then go back if need be and find where the voltage drop is. This is, again, potential to ground. Now, if you have a circuit that has a pulsating current, or in other words, the current's going on and off, there's no way you can do a voltage drop to ground, because the current isn't always on. It's on, it's off, it's on, it's off, it's on, it's off. The only way you can do it is potential point to point. Okay? And you have to use min-max. Okay? You have to use min-max. Once you're hooked up and the system's on, then you push min-max, all right, it'll start recording. As you get your problem develop or whatever, or your glitch or whatever come about, leave the circuit on. Do not shut the car off, because what will happen? All your readings will go out, okay? So it won't do anything. So put your min-max on. Once you've decided your glitch has appeared, you don't have to be watching it. If you could be driving the car or whatever, you don't even have to watch it. Just when you come back, don't turn anything off or anything. Just go to your min-max, hit your min-max, you'll find your minimum, you'll find your maximum, and you'll see what voltage drop, if there's any voltage drop in there. For example, you have a PCM turning something on and off. It's cycling something. All right, like an idle solenoid or whatever, and you're measuring voltage drop. Again, point to point, min-max, one end to the other end of the wire. On the ground side, one end to the other end of the wire. The same thing, because again, even though this has got power in it all the time, all right, it does not have any, if there's resistance in there, right, there's no voltage drop until the current flows, until that computer grounds that wire. And if it's pulsating on and off, you cannot do it to ground. You have to put that point to point. If the PCM is grounding this directly, you can use the potential to ground. Just ground the multimeter. If there's any type of a fluctuation in that, or not fluctuation, excuse me, if it's a pulsating ground at all, you've got to use min-max. Now, here's an injector. That pulses, right? What is an injector pulse at an idle? About 4 milliseconds or so, pulse rate, injector, somewhere around 4 milliseconds. All right? The one thing you have to watch out for on multimeters is your glitch capture rate. If you have a glitch capture rate of 100 or 200 milliseconds on min-max, that means that that meter has to see a problem stay there for 100 milliseconds in order to capture it. How many milliseconds are you looking at here? 4. All right? So if you see a problem in there, all right, if you see, it's going to see a problem, it can't see it. All right? It's too fast. So you want a meter that can go down to 1 millisecond. And I've tried this. I've taken my multimeters, set them at the 100 millisecond range or so, and set up a car battery, take the multimeter with the 2 leads, put it on the battery. I've attached the one side to the battery directly, and the other one I held my hand on it, and hit min-max. Now it's recording, and I sit there and go up and down real fast, as fast as I can. Right? On 100 milliseconds, I got, depending on the meter, I got a little bit of a drop. I got no drop at all, no change, even on min-max. All right? Then I took and set my 1 meter that I have that goes down to 1 millisecond. I set that up, and every time, no matter how fast I took that probe and went on off, instantly went to 0. So that's how fast the 1 millisecond meters can be. All right? The other way to look at it, of course, is at a lab scope. All right, because that's fast, very fast. All right, but if you're looking at things with multimeters, and a lot of guys aren't as familiar with lab scopes, and if you aren't, eventually you should talk to G or whatever and get involved in a class for lab scopes. All right, and but again, doing point to point, wire to wire, and it doesn't matter what side it's on, because again, the only time you're going to get a current, see a voltage drop is when the computer grounds that wire. All right, that's the only time you'll see voltage drop on any of the wires. You have to have current flowing. Any questions so far? Digital storage oscilloscopes. All right, these are your typical lab scopes that are out there. If we're working with them, and we're not using our meter, I don't go over scopes a lot. We just come with some basic patterns on here, all right, just to get you involved in some of this stuff here. If you're looking at, if you hook up your scope and you're on a B plus somewhere on a circuit, and you turn a switch on or whatever, the ignition switch, and it pops up and stabilizes, all right, that's what you should see. Something typical of that. If you see something like this, you've got some sort of a glitch happening there. It's dropping off. If it dropped all the way down to 0, it could be an open, or it could be shorting out, all right? But this is more or less a bad connection somewhere. It could be contacts, or on a relay, it could be anything, all right? And let's talk about different signals. All right, this is a signal typical of a temperature sensor. All right, could be engine coolant temperature. It could be intake air temperature. It could be ambient air temperature. They're all basically the same. Same principle. The PCM puts 5 volts on this, but it's not direct. It's through a resistor, and this is the second resistor in the circuit. So what's it looking for? A voltage drop in the system. And it compares the voltage drop so that it knows what temperature the engine's at. A TPS, for example, all right, it supplies direct 5 volts to the sensor from a 5-volt bus. From a generator, a 5-volt generator, or 5-volt regulator inside the computer. Right? It goes through the resistor to ground, creates a varying voltage drop throughout the resistor. Each point inside this resistor, all right, would have a different resistance, or not a different resistance, but a different voltage. And a wiper wipes across the resistor and picks up the voltage, the differential, anywhere across that resistor, and feeds it back to the PCM as a signal. If you were to short this wire out to ground, what would happen to the voltage here?
0.
Would it go to 0? You short that out to ground. Would anything happen to the computer? Not a thing. If you put this to power, you think anything would happen to the computer? Direct power? Not really, I doubt. Doubt it very much. All right? It was shorted to power. These computers are meant to take a lot. All right? They're designed that these things can happen. They know it. There are some things that weren't designed that well on some of them, but let's say, now this is direct 5-volt reference. Let's say that shorts out to ground. It's going to go to 0. And also, your signal is going to go, no matter where it is on the resistor, is going to go to 0. If this shorts to ground, is it going to do anything to the computer? In most cases, not. Again, if it goes to 12 volts, is it going to do anything to the computer? In most cases, not. All right? Again, computers, when they design them, certain things they expect can happen. Yes?
Even though that's a 5-volt circuit?
That's correct.
12 volts won't hurt it?
12 volts? I've seen them where they've gone to 12 volts. They've shorted to 12 volts. All right? And nothing's happened to it. All right? But the key factor is shorting to ground. If it shorts to ground, all right, the overcurrent protection inside the PCM will stop it from happening. Take for example, Chrysler products, especially, all right, when the crank sensors go bad, all right, they pull it down to ground, all right, you don't get 5 volts on any of the sensors. And that's one of your primary tests, right? You can go to you can't get at that crank sensor, all right, but you can go up to the TPS and put a voltmeter on it and say, I don't have a 5-volt reference, all right? So now you've got to look where these 5-volt supply goes and start either disconnecting sensors or whatever and try to get that 5 volts back. Now sometimes you may have to cycle the computer to get it back, turn the key off, all right, let it cycle and then come back on again, all right? But you get that back, and it won't do anything to it, to the computer, most of the time, all right? Now, again, if we're testing any of the circuits, we can test, since this circuit, the signal wire is grounded, we can test to ground with potential to ground if we know that it's varying, or we can test point to point. All right? Now, on an engine coolant temperature sensor, all right, if you were graphing it and watching it, you'll see it start out at a higher voltage, and as it warms up, it drops off. If you see it dropping off, and then all of a sudden, you see it start to go up like this, what's happening? You're getting a bad connection or an open circuit. It's going towards open. If you get a complete open, where would you expect the voltage to be on a complete open? High, 5 volts. All right, remember, it's being grounded and being brought down. If you get an open circuit, and you're at the signal end of the PCM, all right, it'll go to 5 volts. If the circuit drops out, looks like it should be grounding out doing that. If it goes up like that, goes up that far, what's happening? Shorting to power. Right. Now, after you're stabilized, after the car's warmed up, you get like you should be getting a typical ripple effect in there. Anybody tell me why?
Thermostat's opening and closing.
Not the thermostat.
Cooling fan?
Cooling fan. Okay? Because once that thermostat is opened, it should be stable. It's the cooling fan. Again, what happens is that as the engine warms up, it comes down, the cooling fan comes on at one point, all right, starts to cool the engine. Again, the voltage starts to rise. All right, fan cuts off, starts to go down. And it just keeps cycling. If you're driving along and it's cycling normally, up and down, all of a sudden it drops out to 0. All right? Typical, it's shorting out somewhere. All right. If it goes all the way up to 5 volts and goes steady, it can mean open somewhere. Again, we're working with a 5 volt reference through a resistor or direct 5 volts. And the 5 volt circuit, if you see it drop off, you've got a problem. You see it short out, you've got a problem. You could be driving along and different things happen. This is what you'll see. If you're in that circuit and you're not with a lab scope, you're doing this with min-max in parallel with the wire. If it goes up, it's shorted to power. If you get a lot of hash in it, you've got bad connections in there. All right? Could be interference, but in most cases it's bad connections. Same thing. All right? Now we're going to a TPS. Typical TPS signal, if you're watching it, will start out at idle and go up. If you see it drop off, you got problems. You could be going up normally. This might be a problem, right away. It could be in the sensor, whatever. But if you're going up and you're driving along and you're running along normal while you're driving and you're at a steady throttle and then you start dropping off, shorting out, whatever, could be the signal shorting out somewhere. It's shorting the ground. Hall effect switches, all right? You've got a voltage coming in that turns on the sensor, also runs direct to ground, not direct, but it runs through the sensor to ground, turns it on, and the sensor puts the signal wire, which is usually a 5 volt reference, to ground, creating a square wave each time you pass. It passes on the reluctor. Now, if you have a lab scope on there, you can hook your lab scope, as I said before, up in parallel to a specific wire. The only time you're going to get a signal on your lab scope, if you have a problem there, is when you're drawing current. When are you drawing current? You're drawing a current only when the circuit's on. So if you see your normal square wave on your sensor, the only time you're going to see a voltage drop, if there is a voltage drop in the circuit, is here, where it's at 0 potential. Everybody follow that? Because that's the only time current's flowing. If you're in parallel with a specific wire, you're testing a specific wire, the only time you would see it, if there's a voltage drop, you would see a rise in voltage, is when this is going at 0 voltage, you're down. All right? That's the only time current's flowing. When it's not flowing, you won't get anything. All right? Everybody follow what's happening? Same thing as if you're on min-max. All right? All right. If you're on min-max, same thing. The only time, and it's just going to memorize it. All right? You would only catch the highest peak. All right? But you can see if it's there. On a scope, you'll see all of it. AC outputs. All right? We'll get into the pattern in a minute. All right? But I've had a little problem. I had a code on a transmission for slippage of the torque converter. Torque converter slippage. All right? Guy replaced the torque converter. He replaced the torque converter solenoid. He replaced everything involving the torque converter. And he still had the same code for torque converter slippage. And he called up and he said, what could that be? And I said, all right, let's take a look at the diagram. And I said, how is the computer, and this is what you have to think about, how is the computer determining whether that torque converter is slipping or not? All right. Well, on this particular car, they have the input shaft speed sensor or the turbine shaft speed sensor, which is basically the same thing on the input shaft, all right? And then what they're doing is they're comparing the input shaft or the turbine speed shaft sensor to the RPM of the engine. What should they be when the converter's locked up? Not just steady, but identical. They should be the same. What I found was should be a sine wave like this, AC signal. What I found, and if it drops off, of course, something's happening there, but I found it was lower than normal and had a lot of hash on it. All right? One of the connectors was bad. One of the connectors was bad. And it wasn't the same here as it was here. The RPM signal was a steady signal, and this was not. And it was kicking out a TCC code. Everybody understand how that happens? Yes.
Was that a Chrysler vehicle? Do you remember?
I cannot tell you what it was. I don't remember. I do not remember.
You tested?
All right?
Tested at the PCM?
He tested it at the PCM. Yep.
And
Okay.
the connector that was bad was
At the PCM, at the TCM or PCM.
TS
Okay?
at that connector.
Right, at that connector. All right? Now, O2 sensors. Again, test the wiring normal, all right? But you can test voltage drop, that's fine. You can do it either way, either point to point or to ground. But one thing you check on those is check your amperage. Put an amp clamp right on it. All right? Put an amp clamp on that. All right, because they all run, I shouldn't say they all, but a lot of them run about an amp. Somewhere a little under, somewhere a little over, 1 amp. All right? You could have a spec on it in the book. You may not. All right? But check your amperage. Make sure you have flow. All right? Now, sometimes the amperage, the computer doesn't hold the amperage steady. Sometimes it changes as it warms up. All right? It cycles it. All right? Now we're getting into the wiring end of things. All right? Can everybody see the problem on here? Everybody see this little spot, a little bubble right there? Okay? This was going to, what happened here is, again, as I explained earlier, all right, there was a little pinhole or bubble from the insulation, or the insulation was, the copper was too close to the insulation. Moisture got in there after it was cracked or whatever. Moisture had got into that, all right, and started corrosion inside the wire, and eventually got to the point that nothing flowed through there, or not enough to keep the car running. That was not outside. I had to open up that harness. If you see, I cut that harness open. It was inside the harness, so it wasn't touching anything. Nothing at all. Wasn't touching anything at all.
And no one ever pierced that wire?
Nobody ever pierced the wire. All right? It was just inside. All right? But that's under the hood, and it was near the power distribution block. All right? Under the hood. Now we're going to go into looking for these problems.
It's not under the battery or anything, right?
No, there was no battery corrosion there. No, no, just moisture. And if you look, you could see a lot of moisture on the other wires that were in there if you really looked closely. And but it was just moisture, condensation, whatever got in there. All right. And now we're going to get into I know a lot of people came to me during break about the wire tracers. All right, now we're going to get into that. All right. Wire tracing, we run 2 different types of wire tracers that are out there. All right, there's several other things, but they're all about the same. All right. We have a combination tracer that's put out by Power Probe and Snap-on and a few other places. All right. That does short circuits, and it does open circuits. All right? We also have a wire tracer that primarily does open circuits. Again, super high resistance or open circuits. high resistance and open circuits. Now, one thing you have to remember about when you're tracing, and that is that if you've got wires that are open at end to end, wires that are open, completely open, and wires that are run parallel to the wires you're tracing, they have what they call capacitive coupling. So in other words, if you put a signal into one end of the wire, you should catch it on the other end, and you should be able to do it from either end of that wire and trace it. All right? If there's a break in the wire, because of capacitive coupling, and that wire is open on both ends, it'll trace that wire right through the open circuit, and you won't find it.
It's got to be separated.
If you're running parallel to wires that are also open on both ends, it can capacitive couple to those wires, and you'll get a signal on this wire, and that wire. Okay?
Is there a way to prevent that?
Yes, that's what we're going to get into. All right? So when you're tracing wires, if you put a signal injector in, naturally you're going to pull the fuse because it's not going to, if the wire is shorted or going to power, it's not going to trace it. They do have certain tracers that can do that, very expensive, all right, but most of them we're going to deal with don't do that, but the circuit has to be open, all right? And what you do is if you have a resistance in the wire, let's say, and the wire here is completely open all the way to the end, again, it could be a break or resistance of some sort, you put that signal tracer on it, you'll run this down the wire, and it doesn't matter whether you're using this type or the type like the power probe, they do the same, has the same exact thing, all right? They both have a tip on it, like that, all right? Doesn't make any difference, all right? You're tracing the wires down, it'll trace right through that, right out the other end. You'll never see it there, all right? However, if the circuit is complete, and there's no resistance in there, what'll happen is it'll drown out the signal and you won't see it either. So you have to remember these type of things when you're doing this. Now let's put a complete circuit with resistance in it. Circuit's open up here. You can put an injector, signal injector here. The circuit has high resistance or a break, and the other end of the circuit goes to a load and to ground. Now if you put a signal in here and you trace it down through here, you'll stop exactly here. It will not go past it because you've got a complete circuit to ground. Again, pull the fuse, put the signal injector in here, let's say by the fuse or whatever wire you're tracing. If you have resistance here and the other side goes through a complete circuit, even though it's a load, to ground, you'll trace that right to there and stop. Keep going, pull the fuse, or if it's a connector, pull the connector. You could trace, I trace wires all the time from one end to the other just to find different, where they're connected and things, all right? But, again, let's say you have a break here or high resistance here. If there's a switch here and the load is here but the switch is open, you'll follow this right through the break and right to that switch, and you'll never find anything. If you close the switch so you have access through the load to ground, it'll stop right where the break is or where the high resistance is. Everybody follow that? That's one of the tricks to using wire tracers, all right? If you have, again, the same thing here, you got a wire going to the PCM. It could even be a battery feed. Let's say you've got no battery feed to the PCM, and your fuse is good. Pull the fuse, put the transmitter on there. That PCM is not going to ground. Okay? Inside may not have much of a ground. All right? So put a ground there. Direct to ground. Put your own ground there. All right? Once you do that, you'll run along this line, and right where that is, you'll stop giving a signal. Typical signal on these things here. Somebody must have turned it on, but that's typical signal. Now, I tried to do this up in Connecticut, and they didn't have any fluorescent lights, but if you can, I get it over here very much, all right, but a lot of times they get a lot of interference, all right, from fluorescent lights, so you turn your drop lights and fluorescent lights off, and even AC, all right, so drop lights, extension cords and everything can give that and interfere with it. One thing matter of fact, I didn't mention this in the other class. Boy, I just thought of it. Do you know some computers you can tell when they go to sleep? Because with these things, because in actuality, some vehicles, the PCMs or the body modules, not necessarily the PCMs, but the body modules, before they go to sleep, they have a generator inside that creates quite a frequency. And you can hear them on this. And when they go to sleep, it shuts off. All right? Some cars. You'd have to do your own experimentation, but some cars do. All right?
Is there any signal generator that you recommend out of all the ones you've seen? Do you think one's easy to use or?
Not necessarily.
No, they're all about the same?
They're all about the same. They're all about the same. The only thing I like, what I like is these with the thinner tip, because if you're looking for a specific connector, a wire at a connector, you can trace right to that wire. All right? The thinner the tip, the better. And you can also dig into wires, into harnesses. All right? Okay, everybody else, any questions? Yes?
Is that a phone toner?
It'll also do phone lines, yeah. The phone company uses them like that. And most of them do. Most of the commercial ones do come with a phone jack. Right. All right? Most of the commercial ones. The automotive ones do not. All right? But they work, either one. They're wire tracers. Right. They just work on wires. They don't care what kind of wires they're on. Okay? Now, short circuits. All right? Short circuits are whether you have a positive ground car, and I think positive ground car or a negative ground car, all right, it doesn't make any difference. A short to ground is a short to ground. A short to power is a short to power. All right? And so if we're working on a PCM and any wire that comes out of here, all right, that's shorted to ground is a short to ground. What does short to ground do? What does a short to ground do if it's not checked? Well, there's a PC board, and that just burned out, right? And what's the fix for something like that? That's a fix. Okay? All right, that's a fix. Actually, that caused the problem.
That's smoke harnesses.
Smoking harnesses, yeah. Absolutely. That'll do all kinds of things, all right? Find things like this all the time, though, all right? Well, that's a yellow fuse, right? Okay? It's a yellow fuse. So, and not only did they put wire on it, all right, they used a fuse that was not blown, too. So, boy, that's really ramping that amperage up, available amperage up. Okay? And you could see it kind of melted in there. It kind of distorted when that thing shorted out.
Do you think the current was going through the fuse part of it? The fuse itself? No.
Well, probably some,
Yeah.
all right? It probably, it's parallel there, so some of them went through there, all right? But again, any time we're shorted out direct to ground, short to ground, if wires that are not ground or not B+ are touching each other, that's a crossed circuit. All right? It's not a short, it's a crossed circuit. Now let's get into defining short circuits. That's the other thing that these things do. All right, we got short circuits to this here would blow the fuse. All right, in the main power line to something, when the switch is closed, naturally should blow the fuse, unless you've put a fuse in like that other one. All right, if the short's in the ground side of it, all right, if it's shorted to ground, on the ground side of it, on the pulsating ground side, what will happen? Let's say if that's an injector, all right, what will happen there?
It'll be on all the time.
It'll be on all the time. Anytime the key is on, that'll be on until the injector heats up so much and probably burns out, and then what's going to happen? Then you'll probably blow that fuse. All right? If the PCM is feeding power to a coil, all right, going to ground, and that wire shorts out, what do you think is going to happen at that point?
Might take out the PCM.
It's possible. All right, it is possible. Depends on the PCM. Some PCMs, or if it's a module, say any other type of a module, the same thing. If it's putting power out to something, you could have an input fuse that might blow to the PCM or module. All right, it might blow the PCM, or if it has current sensing capability, the PCM may just shut down. But you're unaware of what, but you still have to find the short. All right, if you're going to find the short, you're going to have to disconnect the PCM. You're going to have to put a signal into the circuit, which we'll go over. All right, here's what we're going to do. All right, most of these are set up so you're going to always run from B plus and put a signal into the circuit with some sort of an injector and pick it up with some sort of a meter. All right, and what we're going to do with this is if you take the fuse out, you put it across the fuse, and you use the tracer to trace it to ground, where the short is, through the harness. If you're going to B plus, all right, rather than the fuse, you can go direct to B plus, put it to any wire, and trace it to where the short is. All right? If you've got a system with a lot of loads on it, if you use the modified amperage, system, okay, you may not have to pull the loads. Matter of fact, you usually don't. But if you use the ones like these that inject a very small signal, all right, they even tell you that you may have to disconnect loads, because depending on the load, it may trace to the load which goes to ground. All right, it may trace several of them. Okay, so if you're in the middle of a circuit, all right, you may accidentally follow something else. Now, they do have a varying, you can adjust the sensitivity on them, but it still can give you a problem, all right, if you're not used to it. All right? One thing you're going to do when you do these things, you're going to look at wiring diagrams. When you look at the wiring diagrams, let's say that fuse blows every time the engine computer, the engine relay, engine management relay is turned on, whether it be from the ignition switch or whatever. The engine management relay, EEC relay, because the EEC relay isn't turned on usually by the PCM, it's turned on through the ignition switch. EEC relay comes on and powers up the circuit. Each time that contact closes, boom, you blow a fuse. All right? Look at the wiring diagram and see, when you look at the wiring diagram, what you think would be the most possibility of a failure, where there would be a most possibility of a failure. And in this case, all right, if you're looking at different things, you've got the fuel pump, you've got the injectors being powered up, the PCM, the mass airflow, coil on plugs, and O2 heaters. Okay? What out of that batch, what would you say is number one?
O2 heaters.
O2 heaters, right. Okay? O2 heaters. All right? They go all over the place. They go down by the exhaust. They're down in the exhaust. The wires go down there, all right? They can rub. I've seen on some vehicles where the O2 heater wiring was wrapped around the drive shaft. Okay? All right? When they do transmissions, they're always down. I've seen them clamped between the bell housing. All right? Things like this. All right? So that's number one, if you just wanted to inspect something, or if you're looking at a specific area to go into. All right? Another area. All right? Naturally, fuel pumps can give problems to an extent, but not the pumps themselves all the time, but where the wires go into the tanks. And remember, those wires run down the rails, all right? That would be probably my number one of the second or third one. But I will tell something also about injectors. Injectors, if they fail, can do something like that. Just like before, if the ground wire was shorted, can cause that. Coil-on plugs, there's a coil suppressor, usually in the B+ wiring. It looks like a little ceramic block. It's really used to use a regular capacitor, what they used to call a capacitor. The can looked like a condenser inside with the points, but it was outside mounted. All right, now they're using them. They're ceramic, they're blocks, and sometimes it's a single wire that goes to that. They might run one or two. All right, and sometimes those wires, people don't realize what they are, all right, and they'll either rub into something or they'll push something against it and short out those wires. Wires near an exhaust, EGR valve or whatever, all right, look at that kind of stuff first, all right. But if you're tracing, all right, you're just going to have to trace out. And if you're tracing, you're going to use either a field tracer like this or a field tracer like that. All right? This tracer would just give you a light, say go this way, or a light that says going this way. This you'll actually see a needle movement one way or the other. If you're using, the newer tracers use a negative tracking meter. This is a negative tracking meter. It's going to track negative. It's going to tell you the ground is this way or the ground is this way. This meter, if it's a negative tracking meter, will do the same thing. The needle will move this way or the needle will move that way. Key factor in tracing shorts with a short tracer. If you have the signal injector in, and whether you're using the needle type or the other inductive type, all right, the other tracer, the same results. Same results. They'll trace a wire even if it's running through the harness. They'll trace a wire as long as the wire is running alone through everything. You could go through a switch, through anything. But if you find there's a bulb socket and there's a short in that bulb socket, the wire that runs up to the socket and the return wire to ground, if you've got a signal, remember it's directional. It's directional. If the signal is saying go this way and the other signal on the other wire is going this way and their wires are close to one another, the signals will cancel out. You'll get nothing. So if you suspect a wire going in a harness, you suspect that you're going one way and the other way, what do you have to do? You have to open up that harness and spread those wires out a little bit and see if you can catch one of the wires going one way and the other wire going the other way. All right? However, if the harness is thick enough and the wire is going, all right, let's say running up one side of the harness inside there and the other side is going the other way, sometimes you can take this or the other meter and you can take it and run it along the harness and go, you might catch the up here, you might catch this direction, and then when you get maybe over here, or go down on the other side, all right, you'll catch the other direction, all right, if the harness is thick enough. You might catch it. Then you know you're going back and forth, all right, because a lot of times what happens is people will follow harnesses at random. They lose the signal here, and then they just go at random around the harness, and all of a sudden they pick it up down here. All right? Now when they pick it up down here, all they're going to do is go to ground. They're at the tail end of the circuit. Now you have to start backtracking. All right? Same thing. Take a couple of little different scenarios here. If you put your signal in here, you're going to track right down here. All right? You don't worry about this ground here because you're not going to short into this ground. The wire is shorted just before the bulb shorted the ground somewhere. It rubbed through and it shorted the ground. All right? But again, let's say it's going to a switch. The signal will go here, fine. All right? As soon as you get to the two wires that go up in and out of the switch, that signal will stop. Everybody follow that? That signal will stop. And when you come down here again, you'll pick up that signal and then follow it right to the short. But what you might have to do is go up and down this wire, all right, again, split it to find out that you're going in and out. On the bottom, same thing. All right, you'll pick it up here. Now you are going to ground down here. You are paralleling through the switch, through the socket, and everything else. So you might catch a signal down here a little bit if it tails down somewhere. All right? But all through here, you're going to have to spread that harness out because you're going one way and the other way. You'll pick it up again down at the end of the harness. All right? I'll have to use this a little sparingly right now. It looks like they're starting to die out. All right? Now, if we're going talk about crossed wires. If we have a battery wire coming into or going out of a fuse block, let's say, to something, and an ignition wire coming out of the fuse block, if they touch, if this is coming out of the ignition switch, and that's direct battery, if those wires touch after the fuse box, all right, that's going to be a short to battery. You'll get battery voltage at the ignition wire, whatever, at that ignition source. You'll get a battery voltage there. If you've got a crossed wire down here, anywhere, you're going to isolate that. You have to isolate the wires themselves that you're getting signals on and put a circuit tester on it and trace those wires out. You can do it if you do it with a short tester, you're going to have to short one of the wires out. If you're doing it with a signal injector, you have to isolate the wires entirely. And again, you may have to short one of the wires out to find out where it is. But if it's direct short, all right, the signal, the wire tracer will not do it. You'll have to do it with a short tester. All right? However, if you've got, let's say you've got a battery voltage here coming in on a fuse box. Your battery voltage goes through on this wire here. All right? Now here's an ignition circuit going to something. Let's say it's going to the computer, the PCM, the BCM. All right? That ignition source is telling the BCM, for example, that the ignition's on. Turn everything else on. Let's activate everything. All right? The fuse block, as I showed you originally before, may have a lot of corrosion in it. If there's a lot of corrosion built up in the fuse block, you could develop, when the ignition is off, some voltage spillover into the ignition circuit. If it doesn't drop below a volt or so approximately, the computer will stay on. That computer will never shut down, never time out. So if you've got corrosion in your fuse block, and I find this a lot, especially on the more sophisticated cars, caddies, things like that, and those fuse blocks under the hood, all right, it could be due to corrosion in the fuses themselves. It could be corrosion at a relay or whatever, and I find that happening. If you've got a drain or something in a car, or the computer's not shutting down, lights shutting not shutting off, things like this here, go to that PCM, see if the ignition, check your wiring diagram, see if the ignition circuit is going to zero. Okay, everybody follow that? Let's go over quickly some PCMs. Again, what to expect. Here's a PCM or TCM, all right? If that switch goes to ground, Okay? Right now, if you were to test at the PCM and test the park wire, what would you see voltage-wise?
0.
All right? How about any of the other wires? What if you went to any of the other wires? What would you expect to find voltage-wise on any of those other wires? I can't hear you. 12 or some sort of reference voltage. Okay? It may not be 12 volts, but some sort of reference voltage. Here's a little different scenario. Now we're putting ignition feed to your range switch. All right? Now it's not feeding the PCM or TCM, you're feeding the cluster and the shift quadrant indicator. Possibly some LEDs up there. All right? And if any of these other wires, except the one that it's on, should now have what? 0. Okay? All right? Should be 0. One other thing they're doing is they're pulling off of the reverse lead, a lead down here going to the backup lights. So it tells the cluster it's in reverse, and it gives the backup lights power. All right? Now, and the cluster is connected to the PCM or TCM via a COM link. What happens if you're driving along and you turn on the headlights? It gets dark, starts to get dark, you turn on the headlights, and all of a sudden that transmission is not shifting right. And all of a sudden you realize that the reverse indicator might be coming on and off or on dim. And if you put a voltmeter on the reverse wire and you're in drive and you have some voltage there, what could the possibility be? Bad ground, bad ground. Okay? Remember something, these reverse lights share a ground with your rear lights in the car. All right? You turn these lights on, all right, and that ground is bad. It's looking for a ground. It's going to back up through the system, all right, and it's going to come up, you're going to get a voltage right up to the instrument cluster. Now what's the instrument cluster going to tell the PCM? I don't know what gear I'm in. It says I'm in drive, it says I'm in reverse.
Doing 55 miles an hour and going backwards.
All right, yeah, okay. All right, so gives you all kinds of problems. All right, this is a cross feed. I'm sorry, this is feedback. Feedback, okay? It's a feedback problem. All right? If we were to take a system like this and in this system here, let's say we were to take a power probe and we were to test this fan by sticking it into the connector and hitting with B+, all right, hitting the power probe to power, all right, what do you think would happen? I didn't too many things at once there. All right?
You blow the breaker.
It would blow the breaker. All right? Because it's grounded. Why do they ground that? They ground it for suppression reasons. All right? When that fan is winding down after it's been on, all right? When it's winding down, it becomes a generator. And it generates power. All right? When the car's driving and the ram air is making that fan turn, also, it's creating power. It can also, when it's generating, all right, it can also give off a little RF. It could generate its own little signal, all right, and they don't want that to happen, so they ground it out. So that motor is now going ground to ground, all right. They ground out the signal, all right. They don't want any interference in anything. Another problem we ran into. Here is the diagram of the circuit on the car. This matches the diagram of a typical Bosch relay, 30, 87, 87A, 86, and 85. All right? This is what the car diagram shows. This is the wiring of the car. Can anybody tell me if I stick this relay in the car, which is the standard Bosch 4-pin relay, or I stick this 5-pin relay in the car, what's going to happen? It calls for a 4-pin relay, right? 1, 2, 3, 4. That's the relay that calls for. But the owner of the car found a relay that fits in here, but it's a 5-pin relay. What's going to happen as soon as you plug that relay in?
The battery.
It won't activate, nope. It'll short to ground. Look what happens. All right? Now, again, here's your battery, 30, load 87. All right? 30, 87. Those are your normally open contacts. All right? 30 and 87 here are normally open contacts. But where does 30 go when it's off? To 87A. What's 87A here? Ground. What's 30? As soon as you plug that relay in, power, that's it. Blows that fuse right there. It'll fit in there. The terminals are correct. Very common problem out there. All right, there's no reason why that ground was there, but the car was wired like that. And if you put the 5-pin relay in place of the 4-pin relay, that's the problem you get. All right, again, a lot of cars have ignition switch that ground rather than put power. They ground and turn relays on. And if that relay's under the hood and you've got corrosion there, when that circuit opens up, the contacts may open up, but if there's corrosion in there, in the relay or whatever, if that voltage doesn't drop to 0 or close to 0, that BCM will stay on. It'll keep the front module activated, rear module activated, could be the battery saver relay activated or whatever, and never shut down. And in the cars, corrosion happens very easily. You've got all these lands. I showed you the picture before of the inside of those circuit boards. All right, like this. All right, you get corrosion in them, forms, and that's it. They get backfeed. They cause crossfeed, all kinds of things. All right, I'm running through these things pretty quick. We still got to get into the thermal imaging. There's not a lot of them, but here's an AC circuit on a car. All right. A lot of people tell me they have problems with AC circuits. Why isn't the compressor coming on? All right, the engine computer looks at a lot of things. Not only does the control head have to send a signal to PCM, all right, the PCM looks at the check engine light. It looks at the ambient air temperature sensor, engine coolant temperature sensor, TPS for wide open throttle. All right, it looks for the pressure sensor, power steering pressure sensor, and it also looks for the system pressure of the AC. Now that's just everything it looks for. There's even some things that I said it looks for the check engine light. There were even a couple of things that the check engine light, even if the check engine light is off, similar things like on Volkswagen, if the throttle needs a relearn, it won't turn the check engine light on, but it won't turn the compressor on either. Okay? And there's a single wire going from the PCM on those Volkswagens to the controller, all right, that if that sends a signal down there, all right, for any reason, whether the check engine light's on or if it needs a throttle relearn, if it sends a signal down there, it deactivates the compressor, all right? Now the signal going into the PCM, all right, has a process too. It has the control head. Let's say that would send a ground to another transistorized circuit, which is monitoring evaporator temperature sensor, evaporator temperature, all right? What happens here is that if this is okay, it allows the ground to continue down to the PCM. But what else is it doing when it's grounding sending a ground signal to the PCM, it's also sending a ground signal to the radiator fan relay. All right? Now, when the system's off and there's no ground here, what would you suspect all these wires to be at? Potential voltage. 12 volts. Okay? 12 volts. It's not a reference voltage. It's getting its 12 volts directly from this fuse here through the coil and into the system because it's not going to ground. It's sitting at 12 volts. All right? Some compressors now have a lockup switch on them, lockup sensor. All it is a set of contacts that work magnetically. All right, set of contacts. It has to see this thing pulsing on and off. If it doesn't see this thing pulsing on and off, all right, it'll shut power down to the compressor entirely. All right. GM, here's General Motors, with every connector and fuse in the circuit, including the fuse link, the fuse for the system, ignition switch, everything. Here's the mode switch and the fan switch. And what happens here is a lot of times guys will complain, or customer will complain, I only have high blower. Where's the first thing you would do if you find on a system like this, you've studied the diagram, I've pulled a lot of stuff out of there and left you just a blower circuit. If you think the blower is bad, or it's not blower, if you say that the blower is only working on high, where would you go first? The resistor, okay? Now if you go to the resistor and you find that you've got no power at any of these, all right? Now where do you go? But you still have high blower. Kind of messed up a little bit there. All right? You say, I'm really messed up. I don't know what the heck to do now. Here's what I would do on this system. I'd go to the fuse. All right? I would turn the system off, and I would probably have voltage of that fuse. Then I would turn the system to high. Turn everything on. Let's say the blower's working on high. Again, I would have some voltage of that fuse. While it's on, I would hit that blower switch and go to any of the other blower speeds. What I'd probably find is the voltage would drop out at that fuse entirely. What's wrong with the vehicle? Can't hear you. No. Nope. Bad ignition switch. Very common problem. The voltage is dropping out. There's not enough power getting through the ignition switch. Buick is one of them. Okay? Okay? Very, very common problem. All right? If the power is there and then drops out when you activate the higher blower, the medium and low blower speeds, all right? Anything other than high, all right? And what's happening is there's enough power getting through the switch to power that little coil on the relay. All right? The little coil on that relay, once it closes that set of contacts, gives direct power to the blower for high. So you're bypassing all of this. Once you activate this end of it, not enough power can get through that ignition switch. All right? Again, the same thing as before. I'll go over it real fast. If there's corrosion in there or anything else, you're going to get front body control module, rear body control module. If they see power or whatever, they're not going to shut down. This is one of the last things before we get into our other part of it. If you're testing any of these switches, you see different resistors in the switches. All right, what kind of voltage would you expect to see on the triggers of these wires? Look at the diagram. They go to ground here, right? Through different resistors. What would you expect to see if they're off on these wires?
Whatever that voltage,
Whatever
the
reference voltage is. Some sort of a reference voltage. All right? Now, if you put the headlight switch, for example, to parking light position, the first position, Now what would you expect the voltage to do? I didn't hear you. It would drop to a specific level. It doesn't matter what level it is at this point, all right? And then if you go to the next resistor, you would see a change. Right, absolutely. You'd see two different voltage changes. You'd see voltage drop, voltage drop. Same thing as right and left turn signal. You'd see one would drop so much, the other one might drop more. Okay? That's telling the BCM it's either right or left, or parking lights and headlights. Does the same thing with wiper motor speeds. All right? Now, the output of that may go to front and rear module to control the lights, or to a flasher and control the lights. All right? It's connected by comlink, though. All right? By a comlink. All right? But that's when you're testing, that's what you're testing for. All right? Here is a system. Anybody work on a Ford variable speed radiator fan? Everybody worked on one? Everybody, have you changed them? Okay. Have you tested them? Been able to test it?
No, the ones that are doing make
You can't. All right? But you can. They say you can't. All right? Now, Dorman makes a replacement fan for them. All right? Comes with the module and the fan. All you have is B plus and ground wires to it, and a little wire goes to the PCM. I called Dorman because I had a problem with a car, and I said, how do you test? I put a new one in, or the guy put the new one in. All right? The shop put the new one in, and it still didn't work. And I said, well, it's a Dorman fan. Let me call Dorman and see how you test this fan, because there was no test procedure on the thing. You know what they told me? The only way to test it is hook it up to a known good PCM. That's what they told me. No test procedure on it. Can't do it. Impossible. And I said, well, I said, that can't be. I got to find some way to do it. We got to test them somehow. All right? What you'll find is the computer uses a pulse width modulation, almost like it does with a fuel injector, and there's 12 volts on this wire all the time. All right, even with the car off. There's 12 volts on that wire. So you can do this test with the car off.
From the PCM or from the fan?
No, from the fan module.
Okay.
Okay, from the fan module. There's 12 volts on that wire all the time. All right? Well, it's very hard unless you have a signal injector, all right, that'll ground that out at the rate needed to test that fan. But I found a way to do it very, very easily. All right? If you take a paper clip or something shaped like a horseshoe or whatever, run a wire to it, and attach it to that wire. Now, it can be connected to the PCM. That's fine. Just attach it to that wire somehow. Take your test light and ground it. Take your test light tip and go like this. Up, down, real fast. It'll give you enough signal to make it work. Now, if you just did a piece of wire to it and tried to do this as fast as this, never do it. But when you do this, you double the speed, because every time when you're doing like this, every time you go up, you don't hit anything. You only connect when you come to ground down like this. But when you put it like a horseshoe, as you go up, it hits the ground. As you go down, it hits ground. So you're doubling the speed, okay? It should make that fan at least start up a little bit, all right? You can't control it or anything, but if it starts up a little, and you know the module is working, the fan is working. Okay? The PCM is bad, or the wire is bad. All right? You do that as close as possible to the module, all right, to test the fan. And then if you want to try it up by here, either test the wire, and that's what I happened. I happened to do it down here, and it worked, and up here it didn't work. All right? There was a break in the wire. Corrosion. Okay?
When you did a Keon test before,
Okay.
did it cycle?
It did not. It did not. So, but I had a test. I had a test for it. All right? All right? This, I think, is the last slide I'm going to give you. Just remember something, not in the program, but we're going into, but here, the last slide here. Some door switches are closed when the door is closed. Now, you're used to switches being closed when the door is open. Some switches now are closed when the door is closed. All right? You'll still get reference voltage on that wire when the switch is, when the switch goes open, when the door goes open. Then you'll get the voltage. When the door closes, switch closes, that voltage will go to 0. Okay? And you say, how can that be? It's drawing power. Don't worry about it. They've got that taken care of. It's virtually nothing. All right? But it happens. Just for your reference, I'm just telling you things that understand what's happening out there. All right? So don't be surprised if you see that. All right? Connections, when you repairs, you can use butt connectors, you can use parallel connectors. Your best thing to do, which you can't do, is spot weld the wires together like the factories do it. All right? Soldering is a no-no. Do not solder wires on cars. All right? Do not solder wires. Several reasons for it. One, makes the wires stiff. All right? Two, all right, the solder joint itself, if it's in a weathered environment, the joint itself will stay solid. But where the solder meets the copper, on both sides will rot right away. Okay? Don't solder wires on cars. All right? It's a fallacy. Wires flex too much in cars. All right? That's why we don't use solid wires on cars. Stranded wires, so they flex. All right? If they're using a crimper, make sure you look at the crimper at the end when you crimp them. Just don't put the terminal on and close your eyes and crimp a wire. The slot in the crimp, if you're using, most crimp connectors have slots in them. Unless you're using an aviation or military grade or whatever you can't have slots in them. All of them, most of them have a slot in them. Put the slot up or down in the seat of the crimper. All right, so when it crimps like this, so you have two sides that are wrapped around. If the slot's on this end, you only have one wrap. And sometimes I see them all over the place. All right? Always put them in the crimper. Watch where your slot is in the crimper, up or down. Use heat shrink. You can use heat shrink, but just remember, even if you use heat shrink, double wall heat shrink with the sealant inside, it doesn't really seal real good against water or moisture. It doesn't make it waterproof. All right? It can keep out a lot of moisture, but not necessarily waterproof. And if you make your connection, leave it up high. Don't let it sag down, because it'll seep in there no matter what you do. All right? And it'll cause. Now, remember I told you repairs before on that connector for that Chrysler blower section there, all right? If you've got a connector like this and it's burnt, all right, the first thing you want to do is get yourself a repair end, all right? Get yourself a repair terminal that'll fit on there, all right, that's going to fit on that tab, all right? Clean that out, cut it out, take the old one off, all right? Pull the wire through if you can. Clean this all out so that a new terminal will slide in and out of there with no problem, all right? If the wire isn't long enough, take another piece of wire, crimp a new terminal on, put the wire through here, and then use a butt connector or something on this end, or a parallel connector. I like parallel connectors better, all right? Then put this terminal onto here before you put the connector on. Put that terminal on, slip it on, and then put your connector on. And it'll slide over it. That's the way to repair it. All right, so if you can't get a complete end, a new end, where you're just going to splice all the wires together, all right, if you can't get that, this is the way to repair it. And and available out there are a lot of even the smaller ends, the 110s, the 187s, the 205s, and of course the 1/4 inch, 250s. All right, but the 110s are available and everything else. So they're all available. All right. I showed you in the beginning. I showed you a lot of problems on the fuse blocks and the relays and where they get hot and they don't hold anymore. All right. If you stick a relay in, it won't last very long. All right. However, some little hints on that. If you take the tabs, it could be a fuse, could be a relay, could be whatever. Take the tabs, take a needle nose pliers, and give it a little twist. I mean, not a lot. All right. A little twist like that, so it's more or less jamming into there. All right. Rather than replacing the whole fuse block, clean it up first. Use a little Dremel tool. Use something to help clean it up to get all the garbage out. All right. And give it a little twist in there. I've also seen people put solder on it. I don't like it as much. But they also make a little tool that can put a dimple in there like that. And on the pins, they put a little S-curve in it. All right. There's some tools that do that on pins that go in. All right. So there are things you can do rather than just, I've seen people jam tin foil in, and that's ridiculous, all right, because that doesn't last for beans, all right? But if you put a little twist in it, that's probably one of the most effective ways of doing it, all right? Put a little twist in it. Here's someone who's put some solder on. Again, you'll see the solder will eventually make a little dip in there, but I don't like that as much as I like twisting the ends, all right? And on printed circuit boards, you see these? Use some good solder, a good soldering iron, not a gun. They overheat too much. Use a nice soldering iron, all right, with a pencil or a chisel tip. Rosin core solder, all right. You could use, depending on the solder they're using there, you could use the non-lead solder, all right. That's a possibility. All right, but then you'd have to take off all the old solder. You'd have to desolder it and use a desoldering gun. All right, but flow some solder in there. Make sure not only is the tip heated up that's sticking through the board, but the board itself, the land on the board is heated up so the solder flows and you get a good solder joint. All right, here we have problems. This was a little overheating problem where they never stripped the wire. When the factory made this, it was a W crimp. The center of the W crimp went through the insulation and made a connection for a while, but then eventually heated up and it just melted all the plastic throughout everything. Here we go into our thermal imaging. This is the last set that we're doing here. All right. Talking about thermal imaging. These units right here. I pick stuff up all the time with thermal imaging. We'll go over a couple of them right now. All right, here's a car, I thought it was a battery drain. All right, same thing. I said, doesn't sound like a drain. Had no drain on the car. I'm looking through the air filter and I'm looking down underneath, through the engine compartment, and I see a hot spot there. How hot was it? It was 108 degrees, and it was only, the car was sitting at about 60 degrees. And that was 108 degrees after a couple of cranks, all right? And what I found down there was this. There's the starter solenoid, all right? Look at those connections, all right? Now, he said to me, but how come the battery's actually going dead? And I said, well, let's see. I said, that tab goes to the battery, that one right there, and that's even melting. You could see the insulation. But this tab right here goes to the alternator. I wonder why it's not charging, especially after it gets warmed up. All right? And a lot of problems there. All right? Here's a battery drain on a Mercedes. Car's been off for 8 hours. Car's been off for 6 or 8 hours. All right? Sitting in the shop. How hot is it there in the center?
Hot.
229 degrees. Okay? What's on? What was that? That was the auxiliary water pump on the rail. Okay? Auxiliary water pump on the rail. All I did was take this thing over, Oh, geez, there's a hot spot right there. Okay? Easily finds a lot of things, these thermal imagers. All right? Here's another battery drain. This is in grayscale only because a lot of times when you're in color, and these do multiple scales. So I went on grayscale on a couple of things just to show people, for example, if it was just seeing a lot of colors, all right, you may not realize what it was, all right. This one you could see a little better. You certainly couldn't tell what those other ones were, all right. This one you can see a little better. If you see it, that's the fan belt of the car, all right. All right. So what is this? All right. All right. Look at the, now I'm not, the dead center is where the temperature up here is. I'm on the outer case mostly, okay. But the scale on the bottom is saying that the coldest spot in this is 75 degrees, but the hottest spot, which is the lightest, which is here, is 202 degrees. That car's been sitting for 6 hours. Okay? All right? So that regulator was holding that alternator. It was full feeling the alternator. It's because it's down inside the alternator. All right? All right? Now the case is warmer, but the inside is... Yep. Right? Okay? All right? Here I'm looking underneath the dashboard at a relay panel, and there's a bunch of relays, but that relay right there, that's on. The computer was keeping the relay on, causing a battery drain. Everybody should pick that up right away. Rear defroster grid. Not only did I find it on a car, all right, I use this thing many times. A guy will say, well, I don't know how good it's working, and I'll find this one's out, that one's out, that one's out. All right? Maybe one or two are working and that's it. All right? Very easy to find that. Okay, guys? You got it. You got any questions? Let me know. All right?